So question 1 asks you to explain the principles, potential use and regulations of drones in agriculture. So first of all, start off with giving a definition. So the definition of a drone is an aircraft or missile that does not carry a human pilot and is therefore piloted remotely. A drone can be called an unmanned or unpiloted aerial vehicle or UAV, a remotely piloted aerial aircraft or an RPA. There are drones which are first-person view, FPV, or remote person view, which is RPV. Both of these two allow the person on the ground flying the drone to see the view as it appears from the drone's perspective, either by looking at a handheld screen or looking through some FPV goggles. So in terms of regulations, drones or UAVs which occupy and operate airspace are regulated by the Civil Aviation Safety Authority, and they've classified the weights of these aircraft into a number of categories. So there's the micro range, 100 grams or less, very small range, between 100 grams and 2 kgs. Small is 2 to 25 kgs, medium 25 to 150, and the large ones are greater than 150 kgs. Now in terms of the safety operating conditions for all RPAs, so first thing is that they may only be flown during the day, not at night. The flyer must always have visual line of sight of the RPA. You're excluded from flying in adverse weather conditions such as fog, heavy rain, low cloud, etc. It must not be flown above 400 feet above the ground, and this is below the minimum flying height for planes or other aircraft, and so that facilitates a buffer zone between RPAs and other aircraft. Another regulation is they must be flown well outside of controlled airspace, such as military zones, aerodromes, airfields. So an RPA must be at least 5.5 kilometers or 3 nautical miles away from any aerodrome or aircraft landing area. For smaller or private airfields, RPAs cannot be flown over runways or the taxiways. In terms of privacy, RPAs cannot be flown over populous areas, such as urban areas, houses, backyards, or even over a group of people. And you cannot fly them within 30 meters of another person, unless that person's helping you. They can't be flown in areas of public safety operations. So, for example, emergency response situations, such as a car crash, if the police are involved, or if there's firefighting, or if there's a search and rescue operation going on. And only one RPA can be flown by one individual at a time. So commercial operators of RPAs with a weight of less than 2 kgs now don't need an operator certificate or a remote pilot's license, but they must advise CASA at least 5 days before their first commercial flight. For private landholders or leaseholders, RPAs can be up to 25 kgs, provided they're operated over their own land, so that would apply to farmers basically. And the last but not least, obviously if you're operating an RPA, you've got to abide by all the conditions that have been set out by CASA. So question 2 asks, what is a multispectral camera, and explain how these operate. So basically a multispectral camera is a camera that's equipped with multiple sensors, as opposed to a normal camera which senses only visible electromagnetic radiation. And so each of these sensors is called a radiometer, and the radiometer measures the reflectance from objects. So some radiometers measure reflectance from red wavelengths, green wavelengths, near infrared, which is 0.69 to 0.9 microns, or infrared, which is greater than 0.9 microns, and or within the red 0.63 to 0.69 microns, or within the green 0.52 to 0.60, or blue 0.45 to 0.52 microns. So each of these sensors is able to specifically measure the reflectance within a specific bandwidth. So most of these multispectral cameras can store the data or the information. And what happens is that information is then downloaded and stored after a flight. Most of these multispectral cameras are small enough to fit in the palm of your hand, and they are basically able to differentiate objects based on that reflectance of those various wavelengths. So for example, the normalized difference vegetation index, or NDVI, is calculated using the reflectance from both the red and the near infrared wavelengths, and we can develop maps using those calculations. So the multispectral camera with several radiometers will capture images of reflectance within several bands of wavelength. A hyperspectral sensor collects the same sort of information but in smaller bands, and therefore it provides much finer detail. So what these images allow us to do is to differentiate patterns within vegetation. So these differences may be due to different vegetation type, or the health of the vegetation, or the presence or absence of vegetation, or perhaps even the presence of disease or pest damage in the crop. So these will show up as patches within the crop. However, the reflectance maps do not tell us exactly what is going on. So we would then go to specific areas and investigate on the ground. And this can then lead to what we call ground truthing. So for example, a certain color may show up as droughted plants. And once we know that that particular color indicates droughted plants, we can probably then utilize that information in later maps if we do them in subsequent years. So these areas of differentiated reflectance are basically the starting points to pay attention to management practices on the ground. They tell us where to look. They don't tell us what's wrong. We actually have to go and have a look and find out. However, if we collect this data over time, these ultimately allow the farmer to develop GPS-based maps, and these then can be linked to variable rate technologies, for example, to address underperforming patches of the crop, and this results in zonal management of the crop as opposed to managing within fence lines. So the use of drones is increasing in precision agriculture over a number of different industries. The question asks you to discuss examples of how drones may be used in precision agriculture. So we've already said that drones or UAVs can be used for cropping or plant-based enterprises, and these carry multispectral cameras. They allow the farmer to do crop mapping. So they allow the creation of, for example, NDVI maps, which can determine pasture availability, for example, and these in turn allow zonal management on the farm as opposed to farming within fence lines. In livestock farming, drones can be used in a number of ways. So for example, they might be used in monitoring infrastructure for maintenance, such as checking watering points, particularly troughs or fence runs, or examining animal housing and buildings. Cameras attached to drones can be used to identify animals that are calving or lambing, or they can be used to determine which animals have been still for too long, or which animals might require some attention. Now, if a GPS ear tag or an EID system is in place, then not only can they tell us the location, but they can also identify that specific animal, so that specific action can be taken to take care of that animal if there's an issue. So drones are currently being tested for mustering of cattle on larger properties, a lot cheaper than using helicopters and multiple staff on horseback. There are cameras that can be used in monitoring livestock in terms of animal health and their welfare. So for example, drones can be used with thermal cameras to measure the emitted energy from the animal, and this thermal mapping can be specifically used to identify animals that might be suffering from an infection. And what you find is that if an animal is infected, their body temperature increases significantly even before any health problems can be identified by eye. And drones can also be useful for delivering or dropping off items, for example, emergency supplies or vaccinations to remote parts of the farm, so they can actually deliver items. So discuss the advantages and limitations of drones with respect to the use of satellite imagery. And this is where you can use your imagination. So first of all, drones have multiple uses. On the farm, for example, satellites do too, but in terms of being able to use that information on the farm, they can be limited. So with drones, for example, these days with the modern robotics, drones can be programmed to drop things off, pick them up, for example, first aid supplies, delivering vaccinations to remote areas in a station. They've even been used to fly out life-saving flotation devices to people drowning before lifeguards can actually get to them. So there are a number of advantages of drones over satellites. And one of the most important things is they can provide access to information immediately. So you can collect the information when you want it, when you need it. So they have multiple uses, so you can use them in cropping, livestock, viticulture, horticulture. So while they can be used to monitor crops and pastures, much like satellites, they can also be used in other activities on the farm, such as infrastructure monitoring with respect to buildings or fences or watering points. And they can be used to roam the farm, to live monitor livestock, for example. So both drones and satellites allow the mapping of a property with respect to using variable rate technologies and obviously optimizing application of resources. But drones enable the ability to get the information that you want, when you want it, when you need it, at a time that suits you. You don't have to rely on downloading information that might only be available every day or every week or every 2 weeks, according to the satellite's orbiting period. And the other thing about drones is that the data from drones can be very high resolution compared to that from satellites. In other words, the pixel size is quite small. However, this does depend on the sensor that is attached. And the reason for that is that because drones operate much closer to the ground than aircraft or satellites in collecting remote sensed information. In terms of disadvantages of of drones compared to satellites, one is that their flight time is dependent on the drone's battery life, and also on the battery life of the camera that's being used to collect the data. So that means flight time is limited by fuel or battery supply. Drones can take more time to cover smaller areas thoroughly, and when using the drone, the amount of information received is likely to be highly detailed, but this then limits the amount of information that can be gathered during any one flight, due to the limitations in computer capacity of the cameras, for example. The drones also will not be able to cover hundreds or thousands of kilometers like satellites can, unless you invest the time and that then costs, of course. With respect to drones, you might need a CASA license. That might cost in terms of training and licensing. But on the other hand, satellite imagery is also not free. The other thing about drones is that they do need repair and maintenance, and that utilizes time, and it can also be quite expensive. So what is Pastures from Space? I'll explain how this operates and what information a system provides to the farmer. So the answer to this question is quite simple, and you can take that from the notes in module 8.4 to compile your answer. However, a useful summary is as follows. So Pastures from Space is a computerized product developed by the CSIRO and the Western Australian Department of Agriculture and Food, with contributions from producers and agronomists, and is now administered by Landgate. So this is a remote sensed online information tool which is available to producers, that is based on satellite imagery of a selected property, and it provides information on pasture growth rates, the amount of feed on offer, the total dry matter, and green imagery, which are the normalized difference vegetation index indices. So it's all built upon the NDVI, as well as various mathematical calculations that run in the background, and this gives estimates for pasture growth rates and feed on offer. With that information, decisions can be made on stocking rates, on feed budgeting, and also fertilizer requirements in producing the pastures for all the livestock in a production enterprise. So Pastures from Space calculates the pasture growth rate from the NDVI imagery, as well as from climatic data from the Bureau of Meteorology, and it uses that information to estimate the plant growth rate in kilograms, the pasture growth rate in kilograms per hectare per day. So where does the NDVI information comes from? It used to come from the National Oceanic and Atmospheric Administration Satellite Imagery, which is an American satellite system which has advanced very high resolution radiometers, which are used to calculate the NDVI. The resolution for these particular satellites is 1.1 kilometer pixels, and the satellites pass around the globe twice a day, which means they supply 14 images a week. Nowadays, Pastures from Space, where possible, uses the MODIS imagery, which is the Moderate Resolution Imaging Spectroradiometer satellites, in place of the NOAA imagery, where possible. This is also available at 14 images a week. However, the advantage of MODIS over NOAA is that the information is available on 250 meter pixels as opposed to 1.1 kilometer, and that means the MODIS data is much higher resolution than the NOAA data. So once the pasture growth rate is calculated on a daily basis, the feed on offer can then be calculated using the NDVI imagery, and that provides the starting feed on offer, and then the pasture growth rate can be applied, and the feed on offer is calculated in kilograms of dry matter per hectare. Now this also uses additional satellite imagery. There are two Landsat satellites, Landsat 7 and Landsat 5. These only pass over the same spot on Earth once every 16 days. However, they have very high resolution, 25 meter pixels. Not only do they use the Landsat satellites, feed on offer is also calculated from the French Spot satellites. Okay, the Spot satellites pass over every 3 to 5 days and has very high resolution, 25 meter pixels. However, having satellite information available on a more regular basis is more expensive than having it available on a less regular basis. So there's a compromise. So the Pastures from Space utilizes multiple satellite systems, and this provides the advantage of obtaining information required when it is required. And so by having those multiple satellite information ensures that the information is always available for the pasture growth rates and feed on offer to be calculated. So when you utilize the program on a selected farm, the imagery will show the paddock boundaries mapped in black. There'll be various colored polygons which will represent the individual paddocks, and the details of each paddock can be shown either by hovering the mouse pointer over the particular paddock or by clicking on the paddock number in the left-hand menu. The default display is for PGR, pasture growth rate, but you can also click on feed on offer and NDVI information by selecting them in the menu. The menu on the left-hand side displays PGR, FOO, as well as the change in feed on offer since the last week, and it also provides the ability to calculate the stocking rate for that particular paddock. And the base information of the pastures from space calculations is the normalized difference vegetation index, or NDVI. So as well as providing the pasture growth rate, the feed on offer, the total dry matter, and the NDVI data at weekly intervals, the Pastures from Space program will also plot that information over the year, and that allows the farmer to see how the current year is progressing and to compare the current year with previous year's information. Of course, historical data is always helpful to make predictions. So all of this information is supported with the use of the rainfall data from the Bureau of Meteorology. And all of this information provided from Pastures in Space, including pasture growth rate, feed on offer, total dry matter yields, NDVIs, and rainfall data, combine to provide both spatial and temporal information. So this tells the farmer where the feed is being produced, when it is being produced, and how much is being produced. And it allows the farmer to identify areas that could be improved or managed differently, or that require extra inputs to improve production. It also allows management of environmentally sensitive areas that perhaps shouldn't be in production, and this altogether results in more efficient pasture utilization. In other words, where the stock should be and when, what needs to be grazed and when, and what improvements need to be made and where. So it provides an objective measure as opposed to an individual person's perspective just by standing at the edge of the paddock.